Hello, today we're going to talk about the pH scale and pH calculations, including kW calculations. Okay, so the pH scale is a negative log scale, and that's because you can get very, very small concentrations of hydrogen ions that are actually affecting the acidity of a solution. So the pH scale became very useful just because it's taking small, teeny tiny concentrations and transforming them into numbers that are easy to work with. So that means when you have a pH scale, we typically talk about it from 0 to 14, with 7 being neutral. Now this is true at 25 degrees Celsius or 298 Kelvin. And anything below 7 would be an acid, and anything above 7 would be a base. Now, these numbers are going to be slightly different when you're at a different temperature, and we will talk about how you can figure that out later, but this will be okay for now. Now, if you have because it's a negative log scale, we take the negative log of the concentration of the hydrogen ions. Okay? That means if you have a concentration of 1 molar concentration, and you take the negative log of that, you get 0. Okay, so negative log of 1 is 0. But then as I start getting smaller, if I have a 0.1 molar solution, and I take the negative log, that gives you a pH of 1. And so you can start to see a pattern. A 0.01 molar solution is a pH of 2. 0.001 molar is a pH of 3. So it refers to kind of the number of decimal places. And when you start writing these in scientific notation, so if I start here, 1 times 10 to the negative 4 is the same thing as 0.0001 molar. That exponent, as long as you're just dealing with 1, that exponent becomes your pH. Okay, so these values here are your pH, whereas these are your concentrations of your hydrogen ions. And they can get very, very tiny. And it's just easier for people, especially just like in commercial business, just like regular people, not chemists, to deal with pH that's from the 0 to 14 scale, rather than dealing with scientific notation, which can be, isolating for people that maybe don't understand it very well. So yeah, have an idea that this is a negative log scale, and each unit on the pH scale is an order of magnitude smaller as you go up the pH scale. Now, there are a number of different ways that you can measure pH. I'm going to talk about 3 of them. You have pH paper or litmus paper, where you have these like strips of paper that have substances kind of built into them that when it gets wet in the solution, it can change color at a particular pH. Works very similarly to an indicator. Indicator, you would add like a drop or a couple drops of the indicator to a solution, and it's going to change color to tell you what the pH is. There are very common indicators listed in your data booklet. This is in section 18 of your data booklet. It lists different acid-base indicators, and it also tells you their approximate pKa and like what colors they're changing between at particular pH values. And then the last major way that we typically measure pH is using a pH probe or a pH meter. They kind of mean the same thing, where it's effectively a conductivity probe, but it's calibrated to measure the pH based on the hydrogen ion concentration. And so the probe or the meter is probably going to give you as long as it's calibrated correctly, it's going to give you the most accurate idea of the concentration of hydrogen ions in the solution. Okay, so let's talk a little bit more about pH calculations then. Our pH is equal to the negative log of the hydrogen ion concentration. And you can actually rewrite that to solve for the H+. If you don't have a base written, you know that pH is equal to negative log of base 10 of the hydrogen ion concentration. I can go ahead and move the negative sign over first. And then to rewrite my logarithm, your base goes on the bottom, and the opposite side becomes your exponent to solve for the H+ concentration. I'm going to rewrite that over here. So hydrogen ion concentration is equal to 10 to the negative pH. Now, if you're not super confident with logarithms and rewriting the logarithms, you can just remember these top two equations, which you definitely need to be able to do both of them, because they could ask you to solve for pH, or they could ask you to solve for the hydrogen ion concentration. So let's say, for example, my H plus concentration is at 3.6 times 10 to the negative fourth. I can type into a calculator negative log 3.6 times 10 to the negative 4, and I will get a pH of 3.44. Now this makes sense because we said 1 times 10 to the negative 4 has a pH of 4. And 1 times 10 to the negative 3 is a pH of 3. So when I have 3.6 times 10 to the negative 4, that fits between the two concentrations. So it makes sense that the pH fits between the two concentrations. Now let's go backwards. Let's say, for example, a problem gives us a pH is 9.04. I want to find the H plus ion concentration. So you would do 10 to the negative 9.04 will give us our hydrogens. And so we would get 9.1 times 10 to the negative 10th, and that's molarity, or you could say moles per cubic decimeter for our hydrogen ion concentration. And it makes sense that this value is very, very small because a pH of 9.04 is pretty basic, so it would make sense you have a very small hydrogen ion concentration. So let's talk about Kw. Kw is called the ion product constant of water. And water can do something called autoionize. Water can break down into hydrogen ions and hydroxide ions. And it does that a small amount normally in pure water. So then from there we can write an equilibrium expression for this. Products over reactants. Our products are the hydrogen ion and the hydroxide ion. And we don't include the liquid water because it's a liquid state, so it doesn't affect our equilibrium position. So this equation is specified as Kw because it's for water specifically autoionizing. Now, because it's an equilibrium constant, it is temperature dependent. So you're going to have a different number of ions of hydrogen and hydroxide at different temperatures. So at 25 degrees Celsius, or 298 Kelvin, let's see if I can write this a little neater. Your value for Kw is 1 times 10 to the negative 14th. And so, excuse me, if you have pure water, pure H2O, a certain amount of it is going to break down into hydrogen and hydroxide, and it will break down evenly. So if I wanted to find it for pure water, I could say that it's equal to x squared because my hydrogen and my hydroxide are equal to each other. And then when I solve for x, I get 1 times 10 to the negative 7th, which is the same thing as the hydrogen ion. And I can take the negative log of that value. Negative log of 1 times 10 to the negative 7th is 7, which gives us our pH, which makes sense that at 25 degrees Celsius, our pH of a neutral solution, when you have equal amounts of hydrogen and hydroxide, your pH is 7. But let's say you're at a different temperature, and it tends to be, at a higher temperature, more of it will dissolve, more of it will break down into ions, so this value is larger than 1 times 10 to the negative 14. So let's say maybe it's, 5.2 times 10 to the negative 14th at this higher temperature. But we know that it's still pure water, and pure water has the same number of hydrogens and hydroxides. So I can still say that this value for Kw is equal to x squared because I know hydrogen and hydroxide are the same. And so then at this higher temperature, I can take the square root, and I get 2.28 times 10 to the negative 7th is equal to x, which is equal to the hydrogen ion concentration. And then I can take the negative log of that value, 2.28, excuse me. And that will give me my pH is 6.64. So I will have a lower pH than it would be at 25 degrees Celsius, but it's still neutral. It's just your whole pH scale shifts. And I know it's neutral because I have pure water and I have the same amount of hydrogens and hydroxides. So it becomes a lot more valuable for us to define an acid as having more hydrogen ions than hydroxide ions, a neutral solution as having equal hydrogens and hydroxides, and a basic solution as having fewer hydrogens than hydroxides. Because this definition is true at every temperature. Instead of just looking at the pH scale of the 0 to 14 with 7 being neutral, that's only valid at 25 degrees Celsius or 298 Kelvin. So be careful there. Okay, so let's do a few example questions. If the pH of the solution increases from 2 to 3, how does the H0 plus concentration change? Let's talk about this for a second. A lot of times you'll see hydrogen ions used the same way as hydronium ion concentrations. That's because when you have hydrogen ions in water, it forms H3O plus. Now, pretty much every time you see hydrogen ions, they're in water. So they're going to be attached to a water molecule and make hydronium. So it doesn't matter whether you say the pH is equal to negative log of the H plus concentration or pH is the negative log of the H3O plus concentration. It means the same thing. So that means if the pH is changing from 2 to 3, so if I have a pH of 2, my H3O plus concentration is 1 times 10 to the negative 2, or 0.01. If I have a pH of 3, then my hydrogen ion concentration is 1 times 10 to the negative 3, or 0.001. So if it's increasing, the pH increases from 2 to 3, my concentration is decreasing by a factor of 10. You'll also see examples like this, as the H plus concentration of a solution with a pH of 5.89, so 10 to the negative 5.89. This gives us 1.3 times 10 to the negative 6th moles per cubic decimeter for my hydrogen ions. Okay, so this one asks us to do a couple different things. What is the OH concentration of a solution with a pH of 4.19? And they tell us that the solution is at 298 Kelvin. Because it's at 298 Kelvin, I can use that Kw value. First of all, let's go ahead and take our pH. 10 to the negative pH will give us the hydrogen ion concentration. So we've got 6.5 times 10 to the negative 5 is my H plus concentration. And then we know Kw is equal to H plus times OH negative. Kw at 298 Kelvin is 1 times 10 to the negative 14th. And we just found the hydrogen ion concentration. I can divide to find the OH concentration. You leave it as brackets. Divide both sides by 6.5 times 10 to the negative 5. So that way it cancels out here. And we are left with 1.5 times 10 to the negative 10th is my hydroxide ion concentration. And that unit is moles per cubic decimeter for concentration there. Now, is this solution acidic, basic, or neutral? Since we know the temperature, we know that 7 is neutral on the pH scale, and this pH is below 7, so the solution must be acidic overall. Okay, a sample of pure water is found to have a pH of 7.24. Is the temperature of the water greater than or less than 298 Kelvin? Well, at 298 Kelvin, we know that the pH of pure water is 7. As the temperature increases, more of the water dissolves. If there's more water dissolving into ions, then you are going to have a lower pH value because you're getting more of those hydrogen ions. So at a higher pH, less of it must have dissociated into ions. So the temperature must be colder. Now, you could also do this mathematically if that reasoning didn't make a whole lot of sense. You can do 10 to the negative pH, which gives us 5.8 times 10 to the negative 8th. which is equal to the hydrogen ion concentration, but it's also equal to hydroxide ion concentration because they told you it was pure water, so you know that they're the same. These values are less than the 1.0 times 10 to the negative 7th concentration that you know would be at 298 Kelvin. And so because there are fewer ions, it must be at a colder temperature because less of it has dissociated. Okay, so this links what is the shape of a sketch graph of pH against H plus concentration. So remember that it is a logarithmic relationship, and it is a negative logarithmic relationship. So if I were to graph this, I will try to do the best I can here, but if this is a pH of 0, 1, 2, 3, 4, 5, 6, like that, and it can keep going. But when you have a concentration of 1 molar, the pH is 0. If you have a concentration of 0.1, so a tenth of that, 0.1, excuse me, that's a pH of 1. A tenth of that would give us a pH of 2 at 0.01. And from here, my graph is not going to scale very well, but it's going to be a tenth each time. And so it effectively approaches 0 without touching. Imagine it's not touching. There we go. Because of that logarithmic relationship. Now it says, when are digital sensors more suitable than analog methods? So pH probes and pH meters are going to be more useful if you need an exact concentration. But they're not super accessible. So digital sensors are definitely more valuable for us in chemistry, like in the chemistry lab, to find specific values of pH pKa, like during titrations. That can be very, very helpful. But if you're like testing your backyard pool water, it's probably not that important to get as specific of pH. You can probably use an indicator with a sample of pool water to test that. And so getting like a general pH might be easier with pH paper or an indicator solution, and a more accessible and easier method to perform. And then it says, why does the extent of ionization of water increase as temperature increases? At higher temperatures, the particles are able to move around more, so it's easier for those to, the water molecules to break up into the separate ions, separate hydrogen and hydroxide ions, which makes sense that because the equilibrium constant is dependent on temperature, at higher temperatures it's going to increase the number of ions present in the solution.